Now let's take a look at an elegant, simple way to represent surface orientation information, and that is called the gradient space. So let's assume that this is your surface right here, z equal to f of xy. At each xy, you know z, which is the depth of the surface. And so we know that the surface gradient is defined as the derivative of z with respect to x. We take the negative of that and we call that p. We take the derivative of z with respect to y, and the negative of that, we call that p. So pq is called the gradient of the surface in our notation. So now we can express the normal at a point, the surface normal, as n equal to pq1, that is negative of the derivative of z with respect to x, negative of the derivative of z with respect to y, and 1. This gives you the surface normal at any point on an object, on a surface. And now if you wanted to find the unit normal, and that is just this normal vector right here divided by its magnitude, so that's pq1 divided by square root of p squared plus q squared plus 1. So pq, which is the gradient, is a very simple way to represent the surface normal at each point using just two parameters. Now let's sort of visualize the relationship between a normal vector and its corresponding pq value. So imagine that this is your coordinate frame right here, x, y, and z, and we're going to consider one surface normal vector right here. This is a unit normal n. So what you do now is that you erect a plane at z equal to 1, which is parallel to the xy plane. So that's a plane at z equal to 1, which is parallel to the xy plane. And then we're going to essentially draw these axes p and q, which are parallel to the axes x and y. This is your pq space, or your gradient space. What does that mean? If you take this unit normal that you see right here, and you simply extend it out to intersect this PQ plane, then wherever it intersects the plane, that is the normal vector PQ1. So that's the relationship between any unit normal vector here and its corresponding to PQ value. So each point on the PQ gradient space corresponds to a unique orientation. So once again, if you're looking at the surface normal, you have the unit surface normal, which is the normal vector n divided by its magnitude. That's defined as follows. We discussed this earlier. But for that matter, you can use the gradient space to describe any direction, the direction of, say, for instance, a light source. So in this case, you have PS, QS1, and so the unit vector in the direction of the light source, this point light source, is S divided by the magnitude of S, and that's PS QS1 divided by square root of PS squared, QS squared, plus N1. Okay, so that brings us to the concept of a reflectance map, RPQ. So in the case of a reflectance map, to compute it, we assume that we are given the reflectance properties of the surface, the BRDF of the surface. We are also given all the information we need about the source that is illuminating the surface. We're going to assume that there's a single source of a certain brightness at a certain distance in a certain direction, S, right here. So what the reflectance map tells you is that for a given source direction S and surface reflectance model, it gives you the image intensity at a point xy. It relates the image intensity that you measure to the surface normal or the gradient at that point PQ. So in other words, once you have the reflectance map, if you tell me what the surface orientation is at a point, I can plug that into the reflectance map and tell you what intensity that surface orientation, that scene point, would produce. Now, of course, we want to go the other way. We want to go from image intensities to surface normals. So let's take the simple case of a Lambertian surface. We've seen the Lambertian surface before. We know that what's unique about the Lambertian surface, well, firstly, it's very commonly found in practice, but what's very unique about it and what's very special about it is that the radiance or the brightness of a Lambertian surface is independent of the direction from which you're viewing the surface. So it doesn't really matter. You illuminate a Lambertian surface, say from the top right here, you're going to get equal radiance in all directions, which is what you see here. The only thing that the intensity depends on is the illumination of the surface itself, which of course depends on the angle of the light source. So as the angle starts increasing, the irradiance of the surface goes down, and therefore the radiance goes down as well, as you can see here. But the radiance remains the same in all directions. Here's an example of a Lambertian-like object, a clay pot. Okay, so we can now describe the reflectance map of a Lambertian surface that is lit by a source in a certain direction and with a certain brightness. So the intensity measured on a Lambertian surface is equal to, this is from the Lambertian model, cosine of the angle of incidence, that's this angle right here between the surface normal and the source direction, cosine of the angle of incidence, times J, which is the radiant intensity of the source, divided by R squared, where R is the distance of the source from the point, times albedo. Albedo we know is the reflectance of the Lambertian surface. Albedo equal to 0 is a black Lambertian surface. Albedo is equal to 1 corresponds to a white surface which reflects all the light that falls on it. So albedo divided by lambda, right here, times C. This C corresponds to, let's call it the gain of the camera. The camera has a certain integration time associated with it, and a lens of a certain diameter, F number. So all of those things get folded into C right here, which is a constant. Now remember, C is known in any imaging system. In fact, in our case, lambda is also known, and J and R are also known because we are assuming we know the light source and we know the reflectance properties. So we can simply assume that C times rho divided by pi times K, K is J divided by R squared right here, which we will call the source brightness. It's a very loose definition of brightness because it folds inside of it, it has the radiant intensity and the distance of the source as well. But C times rho divided by pi times K, we'll simply assume that that's equal to 1. In other words, any image intensity we measure, we can normalize for the albedo of the surface and the source brightness as well as the camera gain. So then we get a very simple expression which basically says that I is equal to cosine of the angle of incidence, and that is equal to n dot s. Remember that n and s are unit vectors. So now we can express this in gradient space. So how do we do that? We know that n is pq1, right? And s is psqs1. So you have the dot product of those two vectors, which is pps plus qqs plus 1 divided by the magnitudes of the source vector and the normal vector right here. And this, by the way, is the reflectance map. This is our PQ. That is, if you give me any PQ, I can plug it into this equation and tell you what brightness it would produce in the image. So let's take a look at this reflectance map. So here is your p-axis, here is your q-axis, it's a two-dimensional space, and in this space we have plotted our PQ. That is, the brighter the point is, the larger the value of R, the reflectance map. So this is what you get. For a source direction given by PSQS, which is right here. That's the source direction in this case. Remember, once again, any point in the space corresponds to a unique direction, orientation. So that's your source direction right here. So you can see here that this is a fairly smooth function, And the question we seek to ask is, what are contours in this map, reflectance map, that happen to have the same brightness? So let's take a look at that. So here's the same expression right here. And now let's go back to our visualization of the gradient space, which lies at z equal to 1 right here. And so let's assume that this is your source direction, unit vector in the direction of the source, S right here. If you extend this out, it intersects the z equal to 1 plane right here, and this right here is PSQS, direction of the light source. So now the question to ask is, what are surface normals, or what are PQ values on the surface, the orientation of the surface, that would produce the same brightness in the image? So for that, we know that the surface normals that for a Lambertian surface that subtend the same angle with respect to the source direction, and those are all the normals that lie on this cone right here, the cone you're looking at. All of these would produce the same brightness value, because for all of those surface normals, cosine theta I is the same. So what you do now is you take this cone and you simply extend this cone out so that it intersects the z equal to 1 plane. That's this. And this ellipse that you see right here corresponds to an isobrightness contour in your reflectance map. So essentially, for the Lambertian case, the isobrightness contours are conic sections. They are intersections of a cone with a plane. And we know that that could be an ellipse, that could be a parabola, or it could be a hyperbola. So that's what we end up getting right here. So if you go back to our reflectance map, you'll see these isobrightness contours. We start with the brightest point in the reflectance map, which is this point right here. We know that for the surface normal that points in the direction of the source itself, cosine theta I is equal to 1, and that gives you the brightest value right here. And then you have these brightness contours where the brightness value falls as you move away from this point. And you have these shapes, conic sections. And finally, the question is, for what PQ values does the brightness go to 0? Well, for that, we can go back to this equation right here and plug in 0 for I. Well, if I is equal to 0, this denominator goes away. So you have P, PS plus Q, QS plus 1 is equal to 0. That's the equation of a straight line. And that straight line is this straight line right here. This straight line right here. So that's an example of a reflectance map. So let's come back to our problem, which is recovering three-dimensional shape from image intensity values. The question that we need to ask is, can we recover the shape of a surface from a single image? So, in other words, if you're given an image I, and you're given the source direction and the reflectance properties, right? We know that the source direction plus surface reflectance together can be combined together to be represented as the reflectance map, RPQ. We've seen that already. So given RPQ and given a single intensity value, can we actually estimate the surface gradient PQ at that particular point? And the answer is no. Why is that? Because if I give you one brightness value at a pixel right here in this image, this is an image of an object, let's take this intensity value. That intensity value corresponds to an isobrightness contour in your reflectance map, such as this one. Therefore, there are an infinite number of PQ values that would have produced the same brightness value. And so we have an ambiguity here. And the whole idea behind photometric stereo is to use multiple light sources to resolve this ambiguity and come up with a unique surface normal at each point on the surface of the object.